In the oil and gas industry, structural corrosion isn't just a maintenance issue, it's a potential catastrophe. We're talking about millions in losses and, more importantly, huge safety risks in pressure vessels.
Exactly.
So today we're diving into a really fascinating model from MA Pascal that uses a hybrid feed-forward neural network to predict these failures with what looks like incredible precision.
And that's our mission here. We want to show you why this model is such a game changer. It predicts the corrosion rate, or CR, and estimates the remaining useful life, the RUL, of these critical parts.
Giving you certainty where before it was mostly guesswork, right?
Pretty much. It's a huge step up from the traditional methods.
Okay, so let's unpack this. Usually engineers either use, simple empirical formulas that aren't very robust, or they run these massive, computationally heavy deep learning simulations.
Right, and there's a big trade-off there.
So what makes this hybrid approach so much more efficient?
Well, it solves that trade-off. It combines the speed of a feed-forward neural network with the foundational knowledge of chemical physics.
How does it do that?
They actually embedded a known corrosion model. It's based on a modified Arrhenius equation right into the FNN.
So the model isn't just blindly matching patterns.
Exactly. It's not just pattern matching. It genuinely understands the underlying chemical dynamics of the corrosion. It's a much smarter approach.
It's a tailor-made network. So what kind of data does this thing need to actually make these predictions?
It takes in 11 key inputs. You can think of them in 3 main buckets. First, you have the operating conditions.
So temperature, pressure, fluid velocity, that kind of thing.
Precisely. The second bucket is what you could call the chemical threats. This includes concentrations of things like chloride, sulfate, oxygen, and of course the pH level.
Okay, that makes sense. And the third bucket?
That would be the historical data. So past wall thickness measurements and some asset-specific corrosion parameters like activation energy and whether microbial-induced corrosion MIC is a factor.
And I saw that to make the model truly robust, they didn't just use the inspection data they had. They augmented it.
Oh, absolutely. This part is clever. They generated 2,000 augmented scenarios by sampling probabilistically around the measured values.
So, like, if the vessel normally runs at 70 degrees Celsius, they train the model on slight variations around that.
Exactly. It forces the model to learn reliable behavior instead of just memorizing a few past readings.
Accuracy is great, but engineers need reliability. I mean, how do we know a prediction isn't just a lucky guess? How did they put confidence intervals around their forecasts?
Yeah, that's the critical question. They used a technique called Monte Carlo dropout.
Dropout is normally just used during training to stop overfitting, right?
It is. But by keeping dropout active during the prediction phase, they could run the model hundreds of times and see how much the answers vary. That variation gives you the model's uncertainty.
So it tells you how confident it is in its own forecast.
Precisely. And the confidence was very high. The uncertainty bounds were tight, averaging only about 0.2 millimeters per year. The error on the corrosion rate itself was tiny.
How tiny?
A mean absolute error of just 0.12 millimeters per year. That gave them an R-squared value, a measure of fit of 0.975. Almost perfect.
Wow. Okay, so this brings us to the most practical finding. Forecasting the future wall thickness. They projected the life of a steel vessel all the way out to 2040.
Right, for 24 different inspection points. And the key takeaway here is the difference between this new exponential FNN model and the standard linear model that just assumes corrosion happens at a constant rate.
And the difference was
significant.
It was huge. The linear model was 3.5 times worse at forecasting thickness. Its error was 0.135 millimeters, while the exponential FNN's was a stunning 0.0389 millimeters.
So what does that actually mean for, say, a plant manager making a high-stakes safety decision?
Well, it completely changes your maintenance schedule. The old, overly conservative linear model predicted that 4 critical sections, the vessel head and a few key nozzles, would be unsafe by 2040.
It predicted they'd fall below the minimum allowable thickness.
Yes. But the exponential FNN, which better captures how corrosion actually works, non-linearly, what did it predict?
It showed that all sections would remain safe through 2040. This moves you from constant crisis planning to a realistic, long-term integrity management plan that aligns with standards like API 5791.
So this deep dive really shows that baking chemical science directly into these neural networks is the path forward for accurate, nonlinear prediction.
It absolutely is, but, and this is the key thought to leave with, this model is highly calibrated to a very specific asset in industrial water. The challenge now is generalizability. To really support the industry, the framework has to adapt to more complex fluids, things containing CO2 or H2S.
So integrating real-time environmental monitoring is the next frontier.
That's the critical challenge ahead for full adoption.